Hi guys, welcome back. So in the second part of the Chapter 5 lecture, we're going to be talking more about energy and enzymes. So there are four types of energy that we are going to be touching on. The first is kinetic energy, which is energy that's associated with motion. The second is thermal energy, which is energy associated with heat. Potential energy, which is stored energy. So potential energy is the energy that's not currently being used in a specific state, however, it has the potential to do so. Now, a common example of what you would see potential energy displayed at is if something is in a standstill state. However, if it were to be changed or if there were to be a change in environment, it could use that energy to help it adapt to those changes in the environment. Now, chemical energy, which is the fourth type of energy we'll be discussing, is essentially a subset of potential energy because it is also stored energy, but this is energy that is stored in chemical bonds specifically and can be used to make chemical reactions go through. Now, in order to understand energy, we have to take a look at energy transformations. And this all relates back to the laws of thermodynamics. Now, whenever we understand these laws of thermodynamics, we can understand more how we cannot simply create energy out of thin air, but rather we have to recycle it. So the first law of thermodynamics states that energy can neither be created or destroyed, but rather it has to be recycled and repurposed and put through its different forms. Now, the second law of entropy deals more with, the second law of thermodynamics deals more with entropy, which is a degree of randomness. So typically the way you would hear this phrased is that the entropy of the universe will continually be increasing regardless of what chemical reaction goes on. So a chemical reaction can go on as long as the entropy of the universe itself is increasing. Now, whenever you think about it put like that, it can sound a little confusing. However, to simplify the second law, we can think that when energy is transformed, the quantity of that energy remains the same, but its ability to do work itself diminishes. So these laws apply to environmental systems because they show us the rules behind how matter and energy fluctuate and recycle throughout the environment. Now, whenever chemical reactions move forward, they can either release or store energy. Now, this can be done either through exergonic reactions or endergonic reactions. Now, in exergonic reactions, it is a net release of energy. So if we take a look at this diagram here, we can see that the reactants have more energy than the products because after this reaction goes through, energy will be released because we're going to have a negative delta G. Now, exergonic reactions are spontaneous reactions because they do have this negative delta G, and they're typically associated with breaking down substances. So I like to think of it in terms of the Lego analogy. So if I have a tower of Legos that is completely built and I want to break it up into its individual parts, it will be like an exergonic reaction because I will be releasing the energy of the bonds that is within the Legos so that I can get back down to the individual parts. Now, my reactants, which would be the tower as a whole, have a lot more energy than the products individually. Endergonic reactions are essentially the opposite of exergonic reactions because these reactions take in energy. So if we take a look at this diagram here, we can see that the reactants have less energy than the products because in order for this reaction to go through, energy has to be input to this system. So going back to the Lego analogy, if I had the individual parts of the Lego and I wanted to put them back together, it would be an exergonic reaction because I'm putting in energy into the reactants so that I can have a more whole product. Now, this is usually associated with building molecules in anabolic reactions because you're starting small and you're working your way up to something bigger. Now, energy and chemical reactions are most often associated with metabolism, which is the total of an organism's chemical reactions as a whole. Now, in a cell, there are many different metabolic pathways, and many of them would not be able to go through if it weren't for energy coupling. Now, what energy coupling is that it takes the energy from endergonic reactions and couples it with energy for endergonic reactions so that the reaction as a whole can go through. Now, ATP is seen as the central energy of a cell, and it drives cellular work by coupling these two different types of reactions together. Now, ATP has phosphate groups, and these phosphate groups are very important because they can be used for phosphorylation. As phosphate groups are lost through hydrolysis, energy will become released. So now these phosphates that are free floating, they can be used in energy coupling because ATP is renewable through cellular respiration. So whenever you break down ATP into ADP and its phosphate molecule, you can also build it back up by putting in an input of energy to make ATP once again. Now, when speaking of chemical reactions, it's important to understand that sometimes we have to increase the speed or the rate at which these chemical reactions can occur. And this can be accomplished by lowering the activation energy. Now, this is the sole purpose of enzymes, and what activation energy is that it's the energy barrier that must be overcome before a chemical reaction moves forward and protects molecules and compounds from spontaneously breaking down. Now, in order to speed up a chemical reactions, you can also increase the heat of the environment that the reaction is taking place in alternative to using enzymes. Now, as we can see here, this is the initial state of the reactants, and this is the final state of the products. However, to get to that final state, we need a certain activation energy to reach that activated complex. But what enzymes allow us to do is release the amount of energy that is required for that to happen. Now, enzymes are needed to break activation energy barriers, and they are highly selective. So, as we can see in this diagram, we have an enzyme and an active site. Now, the active site will only bind to a substrate that is specific to this active site. So as we can see here, in step 2, this substrate, which is sucrose, is going to bind with the sucrase, and it's going to form an induced fit. Now, this can be seen through the lock and key analogy, because if you have a key for a door, the only way that door is going to open is if you have a key that is specifically tailored to the lock of that door. And this is exactly how enzymes function, because if I have a substrate that is present that cannot create an induced fit with the enzyme, the desired product will not be made. Now, enzymes have optimal pH and optimal temperatures at which they can function in order to make their product. And cofactors and coenzymes contribute to the optimal conditions where enzymes can function. Now, even though enzymes exhibit specificity with their substrates, there is still competition through non-competitive inhibition as well as competitive inhibition. So when speaking of non-competitive inhibition, we're going to be talking about an allosteric site, and this can be seen here. So when we take a look at this white molecule, this is seen as a non-competitive inhibitor because it's going to bind to that allosteric site, which is going to create a conformational change in the active site of this enzyme, making it difficult for the substrate to form an induced fit with the enzyme. So although in this situation the actual substrate can still bind to the enzyme, the desired product will not be made because it's not having that induced fit anymore because of the conformational change that has been brought about this non-competitive inhibitor. However, in competitive inhibition, the competitive inhibitor is competing directly at the active site. So here we see that the substrate can no longer bind to the enzyme because this competitive inhibitor has bound to it. Now, the desired product cannot be made because the substrate is not present. Even though the competitive inhibitor has the same shape as the substrate, it does not have the same function. So because structure denotes function, we're still not going to be able to see that product come about. Now, in a normal reaction, you would see that the substrate will just bind to the active site and the product will be made, but these make it harder for that to happen. Now, there is a third type of inhibition, and this is called feedback inhibition. And we can see this through this model. So here we can see that we have enzyme 1, which produces an intermediate, as does enzyme 2, and the ultimate product will then serve as a means of feedback inhibition because it will serve as an inhibitor of the actual first enzyme at the start of the pathway. So this product that we made will then inhibit enzyme 1. Now, to get a little deeper into specific types of enzyme inhibitors, different drugs and pesticides and poisons can be seen as enzyme inhibitors. So ibuprofen, it blocks prostaglandins, and penicillin blocks active sites of enzymes that help bacteria make cell walls. And poisons often attach to enzymes by covalent bonds so that they cannot be reversed. Now, these type of enzyme inhibitors are typically found in the body in high quantities because they also have many therapeutic uses. So when speaking of enzymes and their functions, it's important to understand that there will be several different competitors that will inhibit the function of these enzymes and allow them to work. So now we have covered everything for Chapter 5 in the Campbell Biology textbook. If you guys have any questions, feel free to email them to brhssciencehonors@gmail.com, and we'll see you next time.